All right. So I'm pretty sure we've seen a symbol like this before. That's the radical symbol. And we'll be working with expressions involving these sorts of radical symbols. Before we get to all that, I'd like to explain the anatomy of a radical symbol or a radical expression because that is it's kind of key for things like simplifying and so on and so forth. So if it's not a square root, you'll usually see a number on the legs right here. And generically speaking, we typically write that as n. And this has a special name associated with it. It's known as the index. And it defines the type of radical that you're trying to apply on the inside expression, which this inside expression could be a number, a variable, a mixture of numbers and variables. This is known as the radicand. So I'll write out a few examples of radicals with varying indices over to the right. When n is equal to 2, so if the index is 2, you would see the expression written out, or the radical symbol written out that way. And usually with a square root, we don't include the 2 on the little edge. All right, so if n were 2, the expression over to the left would look like this, and that'd be a square root. If n were 3, that's when you start to see the numbers on the little edge there. You'd write 3 on the ledge, the radical symbol, and then whatever the inside is. And this would be a cube root. If n was 4, write the 4 on the little edge, and this would be considered a fourth root. And you can continue on with larger and larger values of n to define more and more radicals. So usually when you're working with radicals, you simplify things, and that's what we'll do. And we'll also review some properties involving radicals. Now, there's more than what's included in the section of notes, but I went through and just picked out everything that I feel is most relevant to what we'll need to do later on in the class. So at any rate, when you're working with a radical or trying to simplify a radical, you're really trying to figure out what you can raise to a power equal to the index that would give you the inside. So it says here, as a tip, simplify a radical expression, you have to figure out what raised to the power of n would give you the inside expression a. Okay? So the index is important for that reason. You have to figure out what expression or what number you can raise to the index that would give you the inside number. All right? So for instance, with something like the square root of 49, you're trying to figure out, okay, what can I raise to the power of 2? Because that's the index here when it's not written. What raised to the power of 2 would give me 49? 7 would, yeah. Yeah, 7 squared equals 49. So this means that 7 is the square root of 49. Okay, so it's what you can square that serves as your answer. If you look at example B, we have an index of 3, so it's a cube root. So with regard to negative 125, we want to ask ourselves, okay, what can I cube, since that's the index, to get negative 125? Any takers on that? Negative 5, yeah. So if you took negative 5 and you cubed it, you would get negative 125. So because this is the number you cube to get negative 125, the cube root of negative 125 is negative 5. All right, this last example involves a fifth root and a variable expression as the radicand. But the idea is the same. You want to ask yourself, all right, self, what could I raise to the power of 5 to give me x to the 10th? So let's kind of work this one out together. I'll open up a set of parentheses and put a 5 on it. Well, it's probably clear that we'll need x inside the set of parentheses. But if I just leave it as is, x raised to the 5th is not x to the 10th. But keep in mind that, if x were to have a power on it, you would be able to multiply that power to 5. So that's kind of the key here, all right? Is there a power that I could give to x that would turn, the exponent on x to 10? Yep, power of 2, okay? So x squared raised to the 5th does give us x to the 10th, because a property of, or a law of exponents says that you would have to multiply 2 times 5, and that would most certainly give us the 10. So it's this x squared that serves as the 5th root of x to the 10th. So far, so good? Let's keep this gravy train rolling. So what I have next is a table with some properties of nth roots. Okay. First couple of properties are properties that essentially cancel out the radical and the power on the radicand. It says you can cancel that out if the index matches the power on the radicand. Then we have some properties involving some arithmetic inside the radical, namely multiplication and division. And then there's a little bit about what happens if the power on the radicand is different from the index. What can we do in that sort of scenario? And then we'll move on to talking about like radicals. So the nth root of a to the n, if you're able to rewrite anything in the radicand with a power that's equal to the index, then things simplify. Namely, the nth root and the power of n will cancel each other out, and all that will be left over is the expression a. So an nth root will cancel out a power of n. So what that means is a square root will cancel out a power of 2, a cube root will cancel out a power of 3, and so on and so forth. Now, this is a situation when the index is odd with a minimum value of 3. So radicals that have an index of 3, 5, 7, 9, and so on and so forth, because there's a slightly modified result if the index is even. So here we have the same expression, nth root of a to the n, but in this box, we want to consider the index being even. So if you have the index of 2 and a power of 2 on the inside, things will still cancel. But in some cases, what we have to do is put the absolute value symbols around what had that power of n. And the reason for this is because we would expect positive answers to come out of a square root or a 4th root or a 6th root. And if a were a negative number being raised to that even power and the even power canceled out, then we'd be left with a negative number. So this just guarantees that we get positive numbers outside of square roots, 4th roots, and so on and so forth. But usually you don't have to worry about including absolute values. Almost all instructions indicate that you don't have to worry about them. But I just want to include it in there just to be thorough. So the next property tells us what we can do if we're multiplying inside of an nth root. And this works for more than just 2 factors. You could have 3 factors in there, 4 factors, and really as many factors as you want, and the property would hold true for all that. But if you have the nth root of a product, then what you can do is apply the nth root to each factor individually, and then multiply those together. So it's kind of like the nth root distributes. Likewise, if you have a fraction inside of an nth root, you can apply the nth root to the numerator, and you can apply the nth root to the denominator. So in a sense, it's kind of like the nth root distributes across the fraction as well. Now, the very last property looks similar to the first 2 that we discussed, but we're using 2 different letters. So they want us to assume that the index and the power on a are different from each other. If that's the case, then you're not really able to cancel out the nth root and the power of m because they're different values. But you can rewrite this in a couple of ways, which is sometimes helpful. One way that you could write this is the nth root of a, all that raised to the power of m. So in a sense, it's kind of like we can take that power on a outside of the radical. And there are some cases where it's beneficial to do that. We can also rewrite the expression as an expression with a fraction exponent. And here's how you would do that. A, and in the exponent, we'll have m over n. The key thing about the fraction there is the denominator. You are able to rewrite radicals as fraction powers. Just always remember that the index is the denominator of the fraction. Okay, and the numerator of the fraction is the original power that was on a. So as a quick example, if I had the cube root of x squared, and I wanted to rewrite that so that it's a fraction power, you'd write x. The index here is 3, and that's always going to be the denominator. So that leaves you no other choice as to what to do with this 2. That would have to be the numerator. Make sense so far? Any questions? You guys having a radical time yet? All right. So the next thing we'll review are like radicals. And like radicals are radicals with the same index and the same radicand. So for example, oops, come on now. The cube root of 2 and 5 cube roots of 2. These are like radicals. The reason for that is because of the radical expression. Each of them are cube roots, and they have the same insides, or the same guts. Really doesn't matter what's in front of the radical, okay? Even though we have a 5 in front of the cube root of 2, that doesn't take away from the fact that, these are like radicals, okay? Let's look at another example to contrast this with. Square root of 5 versus the cube root of 5. Do you guys think these would be like radicals? Well, keep in mind that they have to have the same index, and the index of the first radical is a 2, right? When it's not written, the index is 2, whereas the index of the second radical is a 3. No worries. So these are not like radicals. So the reason why I'm discussing like radicals is because there are going to be some instances where we might be able to combine radicals with each other via addition or subtraction. And you can multiply radicals together as well. And we'll actually see some instances of that on the next page. But to start things out here, combining like radicals really boils down to 2 rules here, or 2 steps. You want to simplify each radical when possible. And simplification really helps with matters because, with a problem like the one that's coming up, all of the insides of the square roots are different from each other. So at face value, it doesn't look like we have any like radicals, but you'd be surprised at what happens when you simplify the radicals. Usually, a lot of cases, you end up getting like radical expressions. So once you simplify, you want to combine all like radicals by adding or subtracting the coefficients, much like you would with combining like terms with a polynomial. Okay, radicals that are not like radicals cannot be added or subtracted. So for example, if I wanted to add or subtract radical 5 with the cube root of 5, we wouldn't be able to do that. But if I wanted to add the cube root of 2 with 5 cube roots of 2, we would be able to do that since they're like radicals. Okay, so with this example, what we want to do is simplify an expression having 3 radical expressions. And what that means is, try to combine them if you can. All right. At first glance, it doesn't look like we could do any combining. Like I said, all the insides look different from each other. But it turns out that all 3 of the radicals do break down. We can simplify them. So I'm going to start with the first radical, 3 square roots of 48. I'm going to put the square root of 48 inside of parentheses. And what I'd like to do is rewrite 48 as a product. Okay. Now, keep in mind that the index is 2. And the reason why I want to write it as product is because of one of the properties from the table. And this should be a strategic product. You want to pick a product where one of the numbers has a square root. Okay. So I think it might be a good idea to write out some powers of 2 over off to the side. I'll start with 1. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. And that's probably a big enough list to help us out with this problem. So when we're writing 48 or 32 or even 75 as a product, it would be awesome if we could rewrite it so that one of the factors is one of these numbers. And we would want the biggest number from this list that goes into the radicand. So for example, with 48, okay, what's the biggest number from this list that would divide 48? 16. Yep. So that means we could rewrite 48 as 16 times 3. All right, let's move on to the next radical. There's no number in front of the square root of 32, so I won't put it in parentheses. What's the biggest number from that list that goes into 32? 16 again, yep. But this time it's going to be 16 times 2, because that would give us 32. Plus 2, okay, parentheses around the radical 75. Is there a number from this list that would go into 75? 25, yep. We could rewrite 75 as 25 times 3. Now the reason for using these squares, okay, inside of the square root is because they're going to break down to nice whole numbers. For example, this 16, the entire radical could break up as the square root of 16 times the square root of 3. And what that means is that the square root of 16 is going to give us a 4. But there is no square root of 3, so that would be left on the inside of the square root. With the second radical, there's another square root of 16, which would simplify as a 4 going in front of the radical. But there's no square root of 2, so that would have to remain inside the square root. And then with the square root of 25 times 3, the square root of 25 is 5, So what you would see is 5 in front of the square root of 3. Does that all make sense? Do you have any questions about that? So here's what all this turns into. It's going to be 3 times 4, and since the 3 doesn't break down, it's going to stay inside the square root, minus 4 square root of 2 for similar reasons, plus 2 times 5 square roots of 3. Now we have some like radicals, namely radical 3 and radical 3. But there's some numbers in front of those radical 3's that we're going to want to combine before we add things together. Let's go from left to right. This is 3 times 4 radical 3. How you handle that is multiply the 3 and the 4 together to get 12 radical 3. Nothing really much to do with the second term. But we can multiply the 2 and the 5 to get 10 radical 3. So there are 2 like radicals in this expression, 12 radical 3 and 10 radical 3. And because they involve the same type of radical, to combine them, we're simply going to combine 12 with this positive 10. And that's going to give us 22 square roots of 3. And unfortunately, there's no other radical that has a radical 2 involved in this expression. So we'll just have to carry down the minus 4 radical 2 and leave it as is. And that would be about as far as we could go in terms of simplifying that. Any questions? Alrighty. So we'll discuss one more skill, and that last skill for this section is rationalizing denominators. And as you're probably aware, in addition to not liking 0 in the denominator, we also don't like to have radicals in the denominator. And anytime you have a fraction with a radical in the denominator, you're challenged to rewrite the fraction so that the radical in the denominator goes away. Now that doesn't mean that the fraction will evolve into something with no radicals whatsoever. In a lot of cases we end up with a radical on top, which is fine. But the name of the game is just to rewrite it so that there's no more radical expressions in the denominator. And the process that a fraction undergoes so that a radical in the denominator goes away is called rationalizing the denominator. And this skill really makes use of the fact that the nth, not sure why it does that. This skill really makes use of the fact that the nth root of a to the n simplifies to a. In other words, the nth root cancels out the power of n. So let me show you how this is done with a few examples. On example part A, we have 2 over radical 3. Now keep in mind that the index here is a 2. This square root would go away if 3 had a power of 2 on it. But it doesn't. Actually, what's this power on 3 that's in the denominator? 1. So the square root doesn't go away on its own, just with how the fraction is presented to us initially. But we would be able to multiply the denominator by a certain expression which would give us a power of 2 on 3. If I were to multiply 3 by 3, I would get 9, which is 3 squared. But because this 3 is inside of the square root, I can't just multiply the 3 that's not in the square root to a 3 that's in the square root. The only way that we can multiply these two 3's together is if our additional 3 was inside of a square root. So we're going to multiply the denominator by the square root of 3. Now, golden rule of fraction kicks in. Whatever you do to the bottom, you also have to do to the top. So essentially, we're going to be multiplying this fraction by radical 3 over radical 3. Here's what happens on top. Okay? We multiply 2 to the radical 3. Now, because the 2 is not inside of a square root, the best we can do with that is just write it as 2 radical 3. Now on the bottom, because each of these 3's are in a square root, we can multiply the insides together. And what that's going to give us is the square root of 3 squared. What's going to happen with this square root and this power of 2? Yeah, they're going to cancel, and we're left over with 3. So once the dust settles, we have 2 square root of 3 on top, which is perfectly fine. And on the bottom, the square root goes away, as well as the power of 2, and 3 is left over. And voila, there are no radicals in the denominator anymore, and this would be finished. I know it's tempting to maybe cross out the 3 in the denominator with the 3 that's in the square root, but you're not really able to do that because the square root of 3 is what you want to consider, and the square root of 3 is different than 3, so no further simplification. All right, let's try part B. Okay, here we have the cube root of 2/5. To start this out, I'm going to use one of the properties from the table. We can apply a cube root to each of these numbers separately. So we're going to break it up that way. And keep in mind here that the index is 3, and currently what's inside the cube root in the bottom is 5 to the first power. If I want this radical to cancel, 5 is going to need a power of 3. So let's think to ourselves, okay, if I have 5 to the first, what could I multiply this by to get 5 cubed? That'd have to be 5 to what power? 5 to a power of 2. Okay, so this is what we need to multiply 5 to the first by, is 5 squared. But the only way that we'd be able to multiply 5 to the first with 5 squared is if 5 squared is also in a cube root. So we're going to multiply the bottom by the cube root of 5 squared, which means we'll have to multiply the top by the cube root of 5 squared. Make sense? So with that said, let's look at the top. 2 and 5 squared are both inside cube roots. So we get to multiply them together. Okay, that's going to be 2 times 25, giving us 50. Now we do want to keep the cube root surrounding it. And on the bottom, we'll have the cube root. And we get to multiply 5 to the first with 5 squared because they're each in cube roots, and that would give us 5 to the power of 3. And same thing as the last example. We get the radical canceling out the power in the bottom. On top, we'll just leave that as the cube root of 50. It actually doesn't break down any further. And on bottom, we just get regular 5. Any questions so far? All right, let's move on to our last problem for this chapter, our last example for it at least. Here our denominator is a little more complicated. Our denominator consists of 2 terms. We've got 5 and we also have that radical 2. So I would understand if you want to multiply top and bottom by just the square root of 2. Okay, that would get rid of the square root around the 2, but you would also have to multiply the square root of 2 to the 5. So this isn't as easy as just multiplying top and bottom by one radical. We actually have to use something called a conjugate. So I'll make a little note up here. So I'll say given A plus radical B, it doesn't have to be A plus radical B. I could have started out with A minus radical B. Its conjugate, okay, key term there, is A minus radical B. So the two very similar looking expressions. Major difference between them is just what's separating the two terms. The operations between A and the square root of B are opposites. Opposite operations. So you form a conjugate of a radical such as this, or radical expression such as that, simply by changing the operation between the two terms. So the conjugate of 5 minus radical 2 So if we have 5 minus radical 2, its conjugate would be 5 plus radical 2. Now the reason why I'm mentioning conjugates in the first place is because they're actually a key ingredient in order to get the square root gone in the denominator. So we're going to use this conjugate in a special way to do that. What we have to do is multiply the top and the bottom by 5 plus radical 2. Now I'm going to put 5 minus radical 2 in parentheses because there's a special way in which we'll multiply. Right next to it I'll put 5 plus radical 2, and on top we'll have to multiply 5 plus radical 2 as well. So we are still technically multiplying two fractions together. So on top, what we would do is multiply radical 3 to the expression 5 plus radical 2. And the author actually doesn't distribute in an expression such as this. He likes to leave it factored. So I'll leave it factored as well. But do know that you could distribute the radical 3 to each of those two terms to clear parentheses. Now, what's on bottom is a little more involved. We would have 5 minus radical 2 times quantity 5 plus radical 2. And we are going to multiply these together. Anybody have an inkling as to what technique we would use? Yeah, you FOIL. Exactly. Yep. This very much resembles the start of a FOIL problem. So that's actually how you want to handle it. You want to FOIL these out. Now I've been experimenting with a new way of FOILing out expressions of this nature. I do a little box method or like a multiplication table. So I'm going to show that to you guys, and if you want to steal it from me and use it for problems like this, you're more than welcome to. All right, so I'm going to set up some boxes or a little table to the right. It's going to have 2 rows. And 2 columns. And I'm going to label each row with these two terms, 5 and minus radical 2. So I'm going to put the 5 to lead off the first row, and I'm going to put the negative radical 2 to lead off the second row. Now for the columns, I'm going to use 5 in positive radical 2. And essentially, we'll fill out the rest of this table by multiplying the rows with the columns. So for instance, in this box right here, we would multiply 5 to 5. So we'd get 25. In this next box, we would multiply 5 to radical 2. Now because the 5 is not in a square root, it would have to stay out in front. For the bottom row, we're going to multiply negative radical 2 times 5. That's going to give us negative 5 radical 2. And then for the last box here, we'll multiply negative radical 2 to positive radical 2. Now that's a negative times a positive, so the result will still stay negative. And because each of the 2's are inside of the square root, we get to multiply them together, and we get negative square root of 4. Can somebody give me a different version of negative square root of 4? Yep, negative 2. All right. So what do we do with all that information? Okay. Well, basically, we're going to take 25, 5 radical 2, negative 5 radical 2, and negative 2, and add it all together in the denominator. Okay, so I'll write 25 plus 5 radical 2 minus 5 radical 2 minus 2. Now it looks like we still have radicals in the denominator, but do we really? We've got 5 radical 2 and minus 5 radical 2. What's going to happen with these two terms? They're going to cancel. Yep. But there is some stuff still left over, namely 25 and minus 2. We're going to add those together, or subtract them, to get 23. And on top, we'll just continue on writing out that same expression. And what do you notice about the denominator? Do we still have any radicals, or is it all good to go? It's good. Yep, goody in the hoodie. So that's where the pain and torture, fun and excitement for that example ends. And do you guys have any questions about what we did in section R.8?